Welcome to today's lesson on analysis of variance, or as is more commonly known, ANOVA. For today's goals, we will learn how an ANOVA works, make two kinds of figures for data for an ANOVA, run an ANOVA in R, and as always, summarize the results in an R Markdown document. Okay, let's get started. This figure should be familiar to you. It's our data comparing popular names in 1901 by century, half, and sex. In our last lesson, we looked at what happens when you run a multiple regression with an interaction. And we found that our simple main effects are really given certain baseline levels. For example, our effective half of century in our example data was only in reference to when sex was set to the baseline of female. Now, you may rightly be thinking, but I don't want to know the effective century half only for females. I want it for the whole data set. Well, to do this, let's run an ANOVA. As always, let's start with the math. First, what is an ANOVA? Here's the help page for the ANOVA call in R. What I want to draw your attention to is this text here. An ANOVA is a wrapper to LM, or the linear model call. So when we run an ANOVA, we're really just performing a statistical test on top of the linear model we already created. What an ANOVA allows us to do, though, is to look at main effects without having to worry about baselines. So an ANOVA on the data we just looked at would give us the main effect of x1, in our case century half, collapsed across x2, in our case sex, the main effect of x2, or sex, collapsed across x1, and finally the interaction of x1 and x2. So instead of having to run two linear models, one without the interaction to get the main effects, and one with the interaction to get the interaction effect, we can do it all with our ANOVA. What specific test does an ANOVA use, though, to do this? The main statistic in ANOVA revolves around the partitioning of sum of squares. I'm not going to go into detail in this course of how this is done, but here is a brief summary. What's important to know is that the sum of squares measures the amount of dispersion or variability, and then this variability can be attributed to different sources in the various predictors in our model. These values are then used to compute an F statistic, which is probably what you're used to seeing when people report an ANOVA. The higher the F value, the more likely that variable accounts for a lot of the variance in your model, the more likely you have a significant effect. Let's take a second to really break down each of the components in our ANOVA. First, we have our Y value, or a dependent variable, and any independent variables. Remember, an ANOVA is just a wrapper for a linear model, so you must have your dependent variable be continuous. You cannot use an ANOVA on categorical dependent variables. Next, we have what you've probably heard of as an error variable. In most experiments, this is subject or item. Similarly, you also have what I'm calling an averaged variable. Generally, this is whatever variable is not the error variable, which can give rise to people running two ANOVAs for every one experiment, a by subject and a by items ANOVA. To make it a little clearer what I mean, look at the following data. This is our data from before in a format that we can run on ANOVA. We have our Y, or dependent variable, our x1, century half, our x2, sex, and our error variable, specific name. However, originally, this data had one row for each year within each century half. But for our ANOVA, we averaged over years. So our dependent variable is a mean averaging over years given our other variables. We can do the same thing, but switching our error variable and our average variable. Our Y, x1, and x2 are all the same, but now year is our error variable, making our dependent variable averaged over names. If this is a little confusing, that's okay. It will make more sense when you're doing the summarizing of the data yourself. So let's try out some R code for ourselves. Now we'll get our first introduction to doing an ANOVA in R. I've started by putting our multiple regression equation, since again, an ANOVA is just a wrapper on a linear model. Now there are several ways to build an ANOVA in R. One is to use the AOV call. We'll unpack this a bit more in a moment. Another is to use the ANOVA call. But to do this, you must directly feed the call a pre-made linear model. For example, here I made the linear model popnamesinteraction.lm and then fed that into my ANOVA call. You don't have to do this for the AOV call, so we're going to ignore the ANOVA call. Just as for linear models, first we have our Y values, a tilde, then our x1, then our x2, and our interaction term is built in via the use of the star between the variables. Okay, let's look at the summary of our ANOVA. For each of our variables, we have our sum of squares, f-value, and p-values. But you may notice that there are no coefficients. Unlike a linear model, we don't know the direction or size of our effects from our ANOVA. Okay, let's see how our ANOVA compares to our linear models in the last lesson. First, we have our linear model without the interaction, then our linear model with the interaction, and finally our ANOVA. So our ANOVA should look like the model without the interaction in terms of the main effects, since in that model there are no baseline effects, and like the model with the interaction for the interaction itself. We can't directly compare the models since they're using different statistical tests, but we can get a rough idea of how similar they are via the p-values. Indeed, if we look at the p-values for the main effects for the first model, second model, and third model, we see that the ANOVA does look much more like the model without the interaction, particularly for the effect of sex. We see that the p-value is very small for the linear model without the interaction and the ANOVA, but barely under 0.05 for the model with the interaction, which is given some baseline. If we look at the p-values for the interaction, though, we see that they are the same between the linear model and the ANOVA. I'd also just quickly like to point out something else about our linear model and our ANOVA. You may notice that in the full summary of the linear model, there is a summary F statistic to describe the model. If you look at the F values for the ANOVA and take the mean, you'll see it's actually the same as the value for the model as a whole. My goal here is to emphasize that ANOVA really just portioned out the F-score from the linear model to the specific variables, further showing that it's just a wrapper for a linear model. Okay, this is great, but you may be thinking, what about within and between factor ANOVAs? How do I do that? Well, we'll do that by adding an error term. This brings us to part 2 of our math lesson for today. Here's the summary of the AOV call that I showed you before, but there was one part I had hidden. It talks about how we can further add an error term to our model, something we weren't able to do with our linear models. But how do we know if a variable is within or between an error variable? Let's take our 2 data frames from earlier, one with name as the error variable and one with year as the error variable. Let's look first at the by name data frame, and specifically the 2 rows for the name Albert. If we look at our first variable, century half, we see that both levels, first and second, are present. So we would say that century half is a within name variable, because all levels are present within a single name. Conversely, if we look at sex, we see that both data points had the label male, because all names are tagged as being either male or female. So sex is a between name variable, since it's only across several names that all levels are present. Now we can do the same thing with our by year data frame. Let's focus on the year 1901. For century half, only first is present, since year is either in the first or second half of the century. So century half is a between year variable. For sex, though, both sexes can be present in a given year. So sex is a within year variable. So remember that whether a variable is within or between depends on what variable is your error term. Now let's move to the actual R code. We'll start with our AOV call from before, but now we'll add our error term. For this particular data frame, I built it such that name is my error term, and century half, but not sex, is a within name variable. Now let's look at the summary of this model. Our output is a little more confusing than before. In the top part will be any variables that are between names, and the lower part includes all variables that include a within name variable. In our case, that means sex is at the top, and century half and the interaction of century half and sex is at the bottom. Okay, let's see how our new ANOVA compares to our old one. First, here's our ANOVA without the error term, and then our ANOVA with the error term. First, looking at our between name variable, we see that the F value has gotten smaller. However, for our F values for our within name variables, we see the F value has gone up. This relates back to power. Within variables result in larger power, so fewer data points are needed to get significant effects, and thus larger F values. However, similarly, a between variable will result in lower power and a smaller F value. This is why within subject designs are often preferred over between subject designs. Now there's one more thing you may be thinking. I have different numbers in my two groups, and SPSS gives me different values in R. What do I do to get the SPSS values? Well, there are a few ways to do this, but today we'll do it by running an ANOVA with easy ANOVA. And now our third and final math section. Again, here's our standard linear regression equation. Now when R computes the sum of squares for the ANOVA, there are three ways it can do it. For type 1, the order of the variables matters. So when the sum of squares for x1 is computed, it's not taking into account x2, which can be an issue if your data is unbalanced. However, for type 3, order does not matter, and the sum of squares is computed given all variables in the model. Now in R, the default method for ANOVA is type 1, but in SPSS, it's type 3. And this is where the difference can arise between the two programs. Finally, type 2 isn't talked about as much, but basically it should only be used if there is no interaction in the model. I've made this table to try and help understand the three types. See how for x1, the sum of squares is computed differently for each type, whereas for the interaction of x1 and x2, it's the same for all three types. This only matters though if your data is unbalanced. If you have balanced data, which you should when running an ANOVA, this isn't a problem. And now for the last part of our code. To show you the difference, we'll now use the package easy, and specifically the call easy ANOVA. The syntax is pretty different from what we've done in the past. The first thing to note is we specify our data first. You'll notice there is this data.frame call wrapped around the data. Something happens when you modify a data frame with dplyr that makes this necessary when using easy ANOVA. Next, we have our y values, which is our dv, our x1, which is in this case our within variable, our x2, which is our between variable. Now, you may notice there is no place to specify our interaction. That's because easy ANOVA by default does an interaction with all variables. Let's break down each of these settings a little more. dv is the dependent variable, WID is our error term, within is any variables that are within our WID, between is any variables that are between our WID, and then finally, type is where we specify the type of sum of squares. To get SPSS versions, you should set it to 3. Before moving on, I want to make a quick note. This is the summary of what type means in easy ANOVA. As you can see, type 3 is indeed the same as SPSS. However, the authors of this package note that even using type 3 is not perfect. If you don't have balanced data set, you may want to really consider if an ANOVA is the best test for you. Okay, here's our easy ANOVA, which is structurally the same as our previous AOV ANOVA, except set to type equals 3. And here is the summary. As before though, let's compare this to our other model. First, we have our AOV model, and then our easy ANOVA with type 1, type 2, and type 3. If we look at the F values for our x1, century half, we see that they are identical across the four models, as is our F value for sex, and the interaction of century half and sex. This is as expected though, since our data set thus far has been balanced. So what happens if we have the same analysis, and we have the top 20 names for females, but only the top 18 names for males, thus giving us an unbalanced data set? Again, we can compare our four models. Now, if we look at the F values for century half, we see the first three models have the same value, but for our type 3 model, it's different. This is because our type 3 model takes into account the fact that sex is unbalanced for both the main effect and the interaction, while the other models do not. For the rest of the variables, the F values are the same across the models, for sex and the interaction. Okay, so this is one way to have unbalanced data. But what if we do the same analysis, but now sexes are still balanced, but we're missing 4 data points in the second half of the century? Now our data is unbalanced, but in a different way from before. Note, we cannot say that any variable is within, since that's not true for all names. If you try and build a model with a within variable, you'll get an error message. Again, here's our 4 models. Our AOV model is much simpler since we have no error term. Now looking at century half, there's no difference across the four models. But for sex, again, our type 3 model shows a difference while the other three do not. But we still have the same values for the interaction. You may also notice one further new thing, this test for homogeneity of variance. When you have data that is unbalanced like this, Easy ANOVA will compute a test for if your unbalanced groups have the same variance. If the test is significant, it is doubtful that the two groups are drawn from populations with the same variance. Okay, so given all of this, when can I for sure run ANOVA? Well, you need a continuous dependent variable, a balanced data set, although there are ways around this. The same variance must be assumed for each group analyzed, and the samples should be independently drawn. Now, when can I not run ANOVA? If your dependent variable is for count data, you cannot run an ANOVA. Are you taking the percentage of a count? Well, it's still count data. If you have 4 possible options and you transform the answer of 2 to 0.5, that doesn't make it suddenly not based on count data. Okay, let's get to our lab. As you may know, we currently have an election going on in the United States for president. And instead of having any of these fine fictional presidents running, we have this guy running. But instead of talking about the current election, today we'll be talking about past presidential elections. Our dataset comes from the American Presidency Project, which collects data on past presidential elections and terms. Today we'll be looking at the well-known effect that incumbents, candidates who already occupy the position they are running for, have an advantage over a person running for the office as a newcomer. So we'll be looking at elections where one of the candidates was already president at the time of the election. And we'll see what percentage of votes went to the incumbent candidate. But what affects this advantage? First, we'll be asking if the political party of the incumbent, Democrat or Republican, has any effect. For our second variable, we'll need to go over a little United States history. This is my lovely home country, the United States, all happy and together. But we weren't always like that, because in 1861, part of the United States decided they didn't want to be in the United States anymore. And so there were 2 countries. The Union are represented in blue, the Confederacy in red, and in white are any current states that were not a part of the United States at the time of the Civil War. Now, any history buffs out there may point out that these colors aren't appropriate given the time, but they make sense for the overall goal of the lab. So we fought a war to decide if states were allowed to leave the United States or not, and it was decided they aren't. This division has had a lasting effect, though, on American politics that extends even to today. So in addition to looking at incumbent party, we'll also be looking at Civil War country to see if states from the Union or the Confederacy vote differently for incumbents. And finally, we'll see if there's an interaction between these variables. Okay, let's break down our variables. Our Y value is percentage of votes for the incumbent. Our X1 is incumbent party. Our X2 is Civil War country. Our error variable is individual state. And our average variable is election year. Regarding our 2 independent variables, incumbent party is our within error variable, and Civil War is our between error variable. Pause the video now to do the lab. Come back to the video as suggested to learn more about the code in the lab. Now, before I go over how to make a bar plot with error bars, you'll have to sit through my story on why I think bar plots are bad for this type of data. This is some data I created that has the same mean and standard deviation. But as you can see, they're very different. The one on the left has a normal distribution, and the one on the right a logarithmic distribution. And with histograms, this is very evident. Similarly, with a box plot, you can also clearly see the difference, with the long tail and unequal quartiles for the logarithmic box. But if we make a bar plot with error bars, the 2 sets of data look identical. This is why I prefer box plots over bar plots. With bar plots, you lose all the information about the distribution of the data, and even worse, risk not realizing that your data may not be appropriately distributed for a given statistical test. Okay, now that I've gotten my chance to say that, let's go over the code for a bar plot with error bars. The first part of this plot should be familiar to you, as should this part where we set the plot to be a bar plot. In this next layer, though, we add our error bars, using the call GEOM error bar. Within GEOM error bar, we have several parameters. First, within our AES parameters, we set the Y minimum, which is the locations of the bottom of our error bars. Next, we'll set the Y maximum, or the top locations of our error bars. Moving outside our AES, we can set the width of the error bars. Here I've chosen 0.2. And we have to be sure to dodge our position, similar to how we had to dodge the bars themselves. Why it's 0.9 exactly, I can't tell you, but I know that's the magical number that works for plotting error bars in the middle of a bar. Pause the video now and continue with the lab. Before we reformat our data, we'll of course start by setting our old data to a new data frame. Then, we have our filter call to only focus on one subset of the data. After this, we get our new verb, spread, which comes from the package tidier. Spread allows us to spread out a variable into multiple columns. The first thing we'll specify within spread is our variable to be spread out, in our case, incumbent party. So instead of having one column with multiple levels for incumbent party, we'll have several columns to match the number of levels of incumbent party. In our case, 2. So we'll go from 1 column to 2 columns. Next, we have to specify what variable we'll put in our spread out columns. In our case, our dependent variable, pers incumbent mean. So now, instead of having this data in one column, it will be divided as appropriate across our new columns. To make this more clear, let's look at the data frame itself. Here is our data in its post-filtering pre-spread out form. As you can see, we have 2 rows for each state, one for the incumbent party of Democrat and one for incumbent party of Republican. So with our spread call, our data frame will go from this to this. Let's take, for example, our first row in our original data frame. In our new data frame, this row is shown with the column Democrat and the specific value within that column. And the next row in our original data frame is just the Republican column of that same first row of our new data frame. Reformatting our data this way will ensure that our paired t-test really looks at correctly paired values. Pause the video now and continue with the lab. As we end the lesson, I'd like to go over a couple questions you may be having, such as, aren't percentages really just summarized count data, so our dependent variable wasn't appropriate for an ANOVA? Or, we had to drop a bunch of union states to make our data balanced. Isn't that a problem since it was done kind of arbitrarily? Or, for Alabama, we were even missing one Democrat data point. Doesn't that mean our data isn't really balanced? Or, what about the variance for election year? Shouldn't we try and account for that too? All of these are good questions, and they'll be answered and remedied via the help of linear mixed effects models and generalized linear mixed effects models. This marks the end of this lesson. I hope you enjoyed it, and then I'll see you next time.